Hello everyone, this is our lecture 21. Today we'll talk about distributed and low power applications. The difference between what we will talk about today and what we've been discussing so far in terms of traditional communication and computer networks is that today we'll focus on networks that are lower power, mostly distributed, consisting of multiple nodes and sensors that need to communicate with one another, typically through a multi-hop scheme. In the types of networks that we'll discuss today, one of the very important things is energy efficiency because we have limited energy resources. Most of these nodes and devices are battery powered, so we have to make sure that the solutions we have in terms of protocols for different layers are energy efficient so that they can achieve their objective with the least amount of energy consumption. Okay, so let's go over the outline of what we will talk about today. I will first discuss machine-to-machine communications. This is a relatively new concept in communication theory that focuses on networks that consist of a large number of devices that would need to communicate with one another, typically in an autonomous way without human intervention. Very special cases of M2M would be wireless sensor networks as well as SANETs, sensor and actuator networks. And then we'll finish our lecture with some high-level discussion on what are the solutions to energy efficiency for machine-to-machine communications in general. All right, so let's start with M2M. As I mentioned, the idea is that you have a network consisting of a large number of devices that will communicate with one another without human intervention, so typically in an autonomous way. Some of the main features, main characteristics of M2M communications is that you will have a large number of devices, so a couple of devices wouldn't qualify for M2M. Data rates are typically low, so this is not a continuous operation, continuous data transmission. The system is autonomous and is unattended. M2M systems have certain requirements. One of the most important ones is scalability. Because you want to make sure that if you all of a sudden have to add, let's say 10 additional devices, 10 additional nodes, you don't have to overhaul the entire architecture and the system can expand very easily. It has to have energy efficiency because most of these devices are typically battery powered, so you have access to very limited energy resources. You have to make sure you utilize it in an optimal fashion. There are some real-time requirements that are very strict. You have to make sure that your solution, be it for design of different, layer protocols or, routing, things like that. These have to make sure that they will comply with those quality of service requirements. The system has to be very secure, and this is in part because of the fact that the devices are expected to be operating in an autonomous fashion without any human supervision. So you want to make sure that they are resistant against potential cyber intrusions. There are a lot of applications for M2M communications depending on the domain you're interested in. For example, when it comes to various municipal utilities, you can implement M2M in a sense that a large number of meters, let's say in a densely populated downtown area, will communicate with one another, share information, or perhaps collect information at one single point through a multi-hop routing strategy, and then that particular point is going to be connected to the utility communication network. M2M is becoming a hot topic in automotive industry. In the past, there has been a lot of discussion about deploying sensors for vehicle monitoring or perhaps remote diagnostics, but nowadays with the expected penetration of autonomous electric vehicles into the transportation fleet, we are likely to run into a situation that various level 4 and level 5 autonomous vehicles are going to be driving on the roadways, and each one will have a large number of sensors, and for safety purposes you would have to have a situation in which these sensors of different vehicles would communicate with one another to avoid collisions. We can also implement M2M communications in smart buildings, in smart power plants and industrial plants, and smart cities for a variety of different reasons. It could be for added situational awareness and monitoring purposes. It could be for control, distributed control, that is, or for example, very neat and interesting applications for smart cities. I have listed some of them here. One which many of us would appreciate, especially if you come to minds at around 9 a.m. in the morning, would be finding a parking spot. So you could have a situation where a lot of different sensors are located either on campus or on vehicles, and they would share information with one another so that you would know what would be the closest available parking spot to you. And then once you get there, your vehicle can automatically park itself. There are applications in smart cities. People talk about public lighting control, or this one I've listed here, monitoring of roads and bridges. That's actually very, very important. The Federal Highway Administration in the US has a kind of a period of 2 years to assess the health of about 500,000 main and significant bridges. And as you can imagine, this is going to take a lot of manpower, and it's not easy. Now, if you deploy sensors along all these roadways, bridges, these sensitive structures, they can communicate with one another if they identify any issues, for example, with the integrity of the material, or if they notice vibration which is a little bit outside the expected bounds, they can notify one another, and this information can be transferred then to a human operator to perhaps send the crew for further investigation. So these are some examples of M2M communications in everyday life situations. Now, the one thing about M2M is that because of the unique requirements, we typically need to have a different communication technology. Consider this diagram that I'm showing here. I've listed 4 different technologies, or 4 classes of technologies rather. One would be, use this. So one would be your cellular technology. One would be solutions for wireless local area network, for example, solutions based on IEEE 802.11, and then we could look into solutions for personal area networks. We've talked about Bluetooth 802.15.1 and Zigbee 802.15.4. And then we're going to have a potential opportunity for M2M. And as you can see in this diagram, none of the existing technologies would be a perfect fit for M2M. Consider wireless local area networks as well as Zigbee and Bluetooth. These have the shortcoming of not being able to cover the entire geographical area that potentially M2M requires. So M2M, it's possible that would require communication coverage over multiple, hundreds of meters or several kilometers, and neither wireless local area networks 802.11 nor 802.15.1 or 15.4 are appropriate for this. At the same time, we have cellular technology, which of course does cover that geographical area. However, the problem is usage of a cellular technology would be an overkill, because typically the data rate for M2M is going to be much, much lower than what you would expect from a cellular technology. This is still an open area of research in communication networks, and a lot of researchers from around the world are trying to come up with technologies that are particularly designed for M2M applications. Now, the potential topologies, if you implement or deploy an M2M system, could be wired or wireless. Now, in a wired situation, you have individual nodes and machines, which are then connected to a particular gateway, for example, this guy here, through wired or fiber channels. It could be, for example, PLC if we're talking about a power grid situation, or, for example, dedicated fiber channels, twisted pair, coax cable, things like that. Or we could have wireless solutions. Now, when it comes to wireless, we have 2 different solutions. One, which I'm showing on the right, is a centralized wireless. You still have individual nodes that are communicating with a central gateway, but this communication is going to be through a wireless channel. Again, at the moment, our potential technologies are 802.11, Zigbee, or perhaps Bluetooth, depending on the distances. Another potential topology using wireless networks would be a distributed wireless, in a sense that not every node is directly connected to the gateway. Rather, a lot of these communications would have to be through a multi-hop route. So different nodes will communicate with one another, and then they pass the information along all the way to the gateway. There are pros and cons about each of these different topologies. For example, in a wired topology, you can imagine that we have a very good reliability and security in place. However, the solution is probably going to be more expensive. It's not scalable because every time you add one more device, you would actually have to have a dedicated wired channel or a fiber channel connecting that particular gateway to that particular device. In addition to that, it doesn't cover applications in which you need mobility. Now, M2M is not necessarily mobile all the time, but a lot of applications need to have means to support mobility. When you come to centralized wireless, it takes care of a lot of those issues. For example, it's going to be scalable. It's going to be cheaper. However, pay attention here that unlike distributed wireless in the center, here every node would have to be able to directly communicate to that central gateway. This means that they would need to have more powerful transmitters. This is not the case for the distributed wireless. You can have very, very low power transmitters. It's not going to be a problem because individual nodes can essentially talk to one another through a mesh network, and a multi-hop communication forms between that device and the gateway. So depending on the application you have in mind, perhaps the level of mobility that you have, the need for scalability, whether you think that this system is pretty much set in place, or do you expect to have nodes added to it on a regular basis. Depending on these types of constraints, you're going to have to choose from between one of these three topologies. All right, so what I mentioned was M2M is a very general scheme that is used for situations where you have a large number of devices communicating with one another, typically in an unattended human out-of-the-loop fashion. Now, special cases of M2M would be wireless sensor networks as well as SANETs, sensor and actuator networks. Now, not everything that we talked about M2M applies to wireless sensor networks, but there are a lot of commonalities. For example, the fact that these are devices that are relatively cheap, they are energy efficient, they typically have low data rate, and they would have to communicate with one another, typically in a way that humans are out of the loop. These are the commonalities. In wireless sensor networks, typically the distances are smaller than what I showed you in one of the previous slides, where we would have to have coverage up to even tens of kilometers. So typically the distances for wireless sensor networks would be smaller. But there's a lot of similarities between the requirements for a wireless sensor network and what M2M provides to us. In power systems, there are a lot of different applications for wireless sensor networks. In the course project right now, many of you are looking into perhaps collecting data from individual PV panels in a neighborhood, or a series of smart meters, for example, or you may have situations where you have different sensors along the transmission lines to monitor and measure the surface temperature of the conductor. Those situations are typically good candidates for being a wireless sensor network. We can have additional sensors that perhaps monitor voltage and current in various points of the network, monitor temperature, monitor, for example, vibration, or other types of physical variables that are of interest to a power system operator. There are a lot of different applications for wireless sensor networks. One of the most important ones is condition monitoring that can be done for structures like bridges, for example, or in a factory environment. These systems have been implemented in military settings, for example, for tracking the movement of either friendly soldiers or enemy soldiers, as well as having additional situational intelligence. And there are proposals in place to use wireless sensor networks for monitoring and protection of borders. And of course, many people have been deploying those for environmental monitoring, especially now with the trend of having higher frequency of natural disasters with more intensity. It's becoming a lot more important to detect an event earlier. So a lot of countries are working on deploying different sensors, in hazard-prone areas, and these are typically connected to one another wirelessly. They share their information, and if they detect something that needs attention, they would pass it along to the human operator. There are many examples of this. Some countries are using these sensors for prevention or early detection of wildfires. There are some very interesting projects, especially in Italy, which is very prone to landslides, in which they have sensors that sense vibration in the mountain, and whenever a particular set of sensors pick up vibration which is a little bit outside the typical norm for that particular area, they identify this as a potential landslide. They communicate with one another, and then they aggregate the data and send it to, for example, landslide monitoring systems in cities or villages, so that they can notify people who can evacuate very quickly before the actual event unfolds. So these are all perfect applications for having wireless sensor networks, which again is a series of nodes that are distributed, communicate with one another, share information in a wireless fashion. In power systems, I gave you some examples of where wireless sensor networks can be used. This diagram basically gives you a better view. As I mentioned, you can use wireless sensor networks for collecting meter data. You can use it for smart homes, in which we can potentially have multitude of sensors that measure, for example, zonal temperature, zonal humidity, and share this information for a better and smoother control of appliances, for example. Or in a factory environment or in a power plant environment for better monitoring. At the transmission and distribution system level, you can use wireless sensor networks for monitoring overhead lines, underground cables, assets like transformers, shunt capacitors, especially the hotspot temperature of transformers, which is an important aspect in determining how much of its effective lifetime is going to be affected. And of course, in other situations, for example, at the generation level, if you want to monitor a power plant, a wind farm, for example, a solar park, monitor either environmental aspects or perhaps power quality issues. If you want to know, for example, if you have voltage sags at different places, if you have harmonics in different nodes, all these situations can be done by using those wireless nodes. This is a typical structure of a wireless node. You would basically have a energy resource. This could be either a battery or it could be an energy harvester, which we'll talk about it shortly. And then you would have a module which takes care of energy management to ensure that all different tasks and routines within the processor can receive the energy that they require in an optimal fashion. Because again, keep in mind, in these wireless nodes, energy is a very valuable commodity. So it's not something that you have abundance of it. So you have to make sure you use it in a very optimal fashion. The processor can have different modules. It'll typically have a microcontroller to take care of some of the tasks. It will have a memory to run some functions locally, and of course I/O, digital to analog converters or analog to digital converters, and a clock for synchronization purposes. You often have an antenna that allows you to communicate with either neighboring devices or with a central tower, for example. And not to mention the sensing hardware, because most wireless sensors are intended, as the name says it, to measure a particular physical variable. So you would have a sensor, and the sensor would collect that information. You would have an interface in order to interpret this or convert this to a format that is understandable for the processor. Now, I wanted to give you a kind of an overview of some of the technical specifications of a particular wireless node. Just a word of caution, this is not necessarily cast in stone. This is one particular reference that had a very reasonable range of numbers for different aspects or different features of a wireless sensor node. But it is possible, I want to point that out, that it is possible that you have a node in a wireless sensor network that, has values, numbers that do not necessarily fit within this range that I'm given here. But these are typically the numbers you should expect. So in terms of the frequency band, we typically use the ISM bands of 900 megahertz or 2.4 gigahertz, particularly because we don't want to purchase for spectrum. So this is going to be free, and if you remember from our discussions in class, in ISM band, the idea is that everybody is going to access the channel. However, the transmission power is going to be low enough that the chances of interference would be relatively negligible. Having a low transmission power is pretty much a standard requirement for a wireless node. So this would actually be perfect for using ISM bands. Modulation is typically frequency shift keying. Some wireless nodes would actually use the direct sequence spread spectrum technique, which is used in Zigbee, just to make sure that they reduce the chances of interference with other types of communication that is ongoing nearby. The data rates are pretty low, so you don't expect a high volume of traffic going in either direction, typically less than 250 kilobit per second. Memory requirements again are low because they don't do a lot of calculations on site. They mostly capture the information, whatever physical parameter or variable they're measuring. They process that, and typically they send it and transmit it to some other centralized entity who would then use this information for decision-making processes. Voltage level on board is going to be up to 5 volts. And then here I have listed the current level based on the different mode of operation. When the device is in sleep mode, the current that is drawing from the battery is going to be very small. It's about 400 microamps, up to that amount. When it is active, which is the time that it's doing most of the tasks, it would actually be consuming up to 100 milliamps of current. And when it's transmitting information or receiving information, around several tens of milliamps, that would be the current level that it will be drawing from the battery. Now, the reason why I'm providing this, because I want you to be aware that even when the node is receiving information, in other words, even when it's listening to the medium to receive the data from another mode, it's still consuming energy. And again, because energy is a scarce commodity for wireless sensor networks, you have to make sure that that transition between sleep mode, being active, listening, or transmitting is very smooth and very, very optimal and efficient so that you consume the least amount of energy. Now, I guess I touched on this a little bit on the previous slide. Power consumption is a very sensitive topic when it comes to wireless sensor nodes, and you need to pay close attention to it. Most of these nodes, as I mentioned earlier, they have a schedule of going to sleep and being active, so they have a duty cycle. So they are not on for the entire duration of that particular period. If they go to a sleep mode, and especially if that sleep mode is deep, that means most of the functions are going to be disabled. So CPU is going to be disabled, clock is going to be disabled, and so on. Now you might think that this is a good thing, which it is, because it's not going to be consuming a lot of energy. However, keep in mind that there is no free lunch. When your node goes to a very, very deep sleep, meaning that all these functions are disabled, when it wants to transition back to the active mode, it's going to take a lot longer time. So this transition, if you need the node to be able to switch back and forth very, very quickly between sleep mode and active mode, then that requires that having a deep sleep mode is probably not an ideal situation, because it basically makes the transition a little bit slower. These are again things that you would have to decide on, and it's going to be a design trade-off. When it comes to designing a wireless sensor network, there are a lot of challenges that you should be aware of. First and foremost, your solutions in terms of protocols and products have to be interoperable. Make sure that you do not use proprietary solutions, because that can severely impact the scalability of your solution or your system. Memory consumption is another challenge. We have to make sure that the protocols that we use are simple and have low overhead, because you typically don't have a lot of memory on board. And at the same time, if you're dealing with protocols that are very heavy and have a lot of overhead, for example, headers that are long and have multiple fields that need to be assessed very carefully, this of course translates into higher energy consumption. So this is something you want to be aware of. Power is a very, very important constraint in design of wireless sensor networks. People typically focus on protocols that are energy efficient. Again, as I mentioned, they have low overhead. They work on different mechanisms for energy conservation, as I mentioned on the previous slide. For example, deciding on an optimal schedule between having a sleep mode versus an active mode and transitioning between the two. And of course, a lot of people have started looking into using energy harvesting techniques, so that instead of using batteries, you can use the energy resource which is available in the environment. Security is important, because wireless sensor networks, just like machine-to-machine communication networks, they are typically consisting of wireless nodes that are unattended, so you won't have a human operator supervising that all the time. So you want to make sure that your design is secure against any potential cyber intrusion. Your protocols are secure. Your data link layer protocols and MAC layer protocols have to be aware of the unreliability of wireless links. So they should do routing in a way that it is aware of the quality of the links between different nodes. So if you have links that, for example, typically are unreliable and the information doesn't go through very effectively, that particular link has to be given a weight in such a way that it's going to be as much as possible removed from routes that go, for example, from point A to point B. Data management is important. As much as possible, you would like to aggregate data and compress data in order to make sure that the size of data packets that you send are going to be smaller, hence taking less time for processing. And of course, any type of protocol that you use, you have to make sure that your protocol is scalable, so that once you increase the size and dimension of the system, you don't have to go back to square one and redesign the entire system from scratch. There are a variety of different topologies again. One particular topology is star, in which you have different sensor nodes that will communicate to a coordinator. By this point, I'm assuming you have a lot of examples in your mind as related to power systems. For example, this could be in a sense that you have a data concentrator in the middle of a neighborhood that is directly communicating to individual smart meters. It is also possible to have opposite of that, which would be a mesh network on the right, in which different devices communicate with one another, and almost every communication is going to be multi-hop. So it has to go from one node to another to another. This one is going to give you a higher level of scalability, and as I mentioned earlier, you will have lower power transmitters instead of having a star topology in which every node has to have enough transmission power to be able to communicate exactly to the coordinator. We can have something in between as well. We can have situations in which different nodes will communicate to one node which collects all this information, aggregates it together, and then forwards it to the coordinator. This is kind of something in between, because these nodes on the periphery can be low power, but the forwarders have to have enough power so that they can transmit the data directly to the coordinator. In terms of the protocols to be used for different layers of network architecture in wireless sensor networks, much of the focus is on two things: designing an efficient medium access control or MAC layer protocol, as well as designing efficient algorithms for routing. For MAC, our focus is on energy efficiency. We have to make sure that the protocols are light, they don't have a lot of overhead. So again, you want to make sure that your header is small so that you don't utilize a lot of energy to examine different parts of a header. The usage of acknowledgements can actually be a little bit problematic because typically the payload is very small in such a way that a lot of times the size of the header and the size of the payload are comparable. So if you send the information and wait for an acknowledgement, this is going to take pretty much, the acknowledgement is going to take pretty much the same amount of bandwidth that the original message did. So this could be problematic. You want to make sure that the packets are as small as possible. We're not too much concerned about collisions. If they do occur, of course, they are wasteful of the power and resources that are very limited in wireless sensor networks. However, collisions are not very frequent because, again, as I mentioned before, in these networks, the data rate is pretty low, so the sensors do not continuously send information. The frequency of sending information, sending and receiving it, is pretty much lower, so chances of collision would be lower as well. A few other things that you would be aware of: over emitting. This is something that leads to a wasting of the energy resource. This is when your node, the transmitter node, is transmitting data, but the receiver is not active, is in the sleep mode, so essentially is not hearing it. So that's wasteful of your resources. Another problem is idle listening, in which you as a receiver node are actively listening to the medium to see if there is any information intended for you, any signals are intended for you. But if you remember from one of our previous slides, the amount of current that you consume even during idle listening is going to be relatively high. So this is again something that you want to optimize. Overhearing is another term that indicates sending messages to everybody, for example, through a broadcast scheme. However, all the nodes are going to be hearing that message, but this message perhaps is not going to be intended for all of them. Meaning that a lot of them are unnecessarily listening to this message. So that's another thing that we try to avoid as much as possible. When it comes to routing, there are a lot of interesting approaches, interesting algorithms to enable route identification between a sender and a receiver. Keep in mind that in particular, if these wireless nodes are mobile, that means the structure of the network is changing all the time. So this complicates the situation with routing. In most cases, routing is going to be in the form of a multi-hop routing, so you don't really have like a direct connection between the sender and the receiver. You have to make sure that your routing algorithm is able to deal with situations where, for example, one node all of a sudden goes out of service. If the node goes away, the route that it was a part of before is not going to be operational anymore. So these are the types of things that you will have to be aware of. There are different technologies that we can have, again, as very similar to the diagram I showed you before. We can have direct routing. This is a single hop situation in which individual nodes communicate directly to a coordinator. You could have a multi-hop approach, which is flat in a sense that, like a mesh network, different nodes communicate with one another until the information gets to the coordinator. Or you could have a clustered or a hierarchical mesh network in which you have, similar to the diagram I showed you before, where individual nodes communicate with the forwarder, and then forwarder will forward this information to the central coordinator. So this is the same concept. So taking wireless sensor networks one step further will be SANETs. So SANETs are very, very similar to wireless sensor networks, except for the fact that in addition to sensors, they have actuators. So not only they can be used for applications in which we need monitoring and situational awareness, they can be used for applications we need for distributed control. They can be used for distributed control in factory environment, in smart homes, in smart buildings, for distributed dispatch of energy resources, for demand side management inside a smart home where you would like to have, for example, zonal air conditioning, zonal humidity control. So SANUS would be a perfect solution for that type of application. SANETs essentially consist of sensors that could be electrical sensors for measuring voltage and current, or sensors to measure other physical parameters and variables like temperature, vibration, humidity, and occupancy, which is a very important one for smart homes. And your actuators then would be, for example, motors, breakers, valves, things like that. So all of these would be connected to one another, typically in a wireless fashion, but a wired version of it is possible too. Now, before we close this lecture, I wanted to talk to you about two kind of more advanced solutions for energy efficiency. As you saw in our discussion on M2M communication networks and wireless sensor networks, one of the biggest challenges is energy efficiency. We have limited power and energy available, and we have to make sure that we optimize its utilization rate. One way to do this is through usage of compressive sensing. In compressive sensing, essentially what you try to do is you try to take advantage of the spatial correlation and temporal correlation between data points to avoid sending unnecessary information. Let me give you an example. If you have a heat wave condition in a power distribution system and you have one overhead line that is stretching, let's say 30 miles, 40 miles, and you have a large number of sensors that are connected along this line and forming a wireless sensor network, for example, because of the uniformity in the temperature, if one of these sensors indicates that there is an excessive surface temperature for the conductor, chances are for the other ones the situation is going to be the same. So you probably don't need to send all the information to the control center. Perhaps one of these sensors can be a good representative of everybody else. In some other situations, if you have enough memory and computational power locally at every node, what the node can do is, instead of sending the entire information, it can compress the information so that it has a much smaller size packet. So that's another thing that we can do. The benefit of using compressive sensing would be energy consumption will go down, and you will use your computational resources much less. So this actually extends the life of your battery, for example. And of course, in situations where you have a large number of sensors, something happens, everybody wants to sense its information, potentially creating a bottleneck. By doing compressive sensing and aggregating this information, or perhaps even not sending unnecessary information, you will avoid having those bottlenecks in the data communication. Another very interesting solution for energy efficiency that a lot of researchers are looking into is energy harvesting. The idea behind energy harvesting is to utilize the ambient energy that is available to you. Basically, if you have enough energy available locally, it might allow you to run your sensor node without even having a battery. If you don't have enough energy available, that would mean that your energy harvesting source is going to be in conjunction with the battery. So that typically means that the life of your battery the remaining life of your battery will increase because you're not going to be utilizing it as much. When you want to use an energy harvester as the main source of power supply for a wireless node, there are a few things that you have to be looking into carefully. For example, this source of energy, is it something that is always available, or is it something that is available during certain hours of the day? For example, if you're using a solar powered device, solar power is essentially a form of energy harvesting, but solar radiance is not going to be available at nighttime. So that is something that you need to be aware of. Second question, this source of energy that you have in the environment, does it vary in intensity? Is it something that its availability goes up and down, or is it relatively fixed during the day and night, for example? Another question is, how many sources do you have that you can take advantage of? This is something that a lot of people are looking into, and it's a very interesting approach because typically the amount of energy available through energy harvesting is pretty low. So that means that you may need to think about having more than one energy resource and combine the total energy in order to be able to power your node without a battery. So that's another question to look into. And of course, the very, very important one, this energy harvesting solution, is it cost effective? Because it is true that it extends the remaining lifetime of a battery, but if it turns out that it's a very, very expensive solution, then it's not, there is no good justification for using it, then that's not going to be a good alternative, and you're better off just using a battery, as is the case in most standard wireless nodes. On this slide, I wanted to give you a sense of how much energy we're talking about. There are different sources for energy harvesting. The three that I have listed here are thermal energy harvesters, solar energy harvesters, and vibration-based. Vibration is also known as mechanical energy harvesters. So as you can see, I'm not going to go through all the rows and columns of the table. This is something for your reference, but essentially I want you to pay attention to the various amounts of energy that is available based on the type of source that you're using. Thermal energy harvesters are very neat. This is a project that one of my former master students worked on in the past. We built a device that could use the temperature differential between a hot side and a cold side, and then converted it to electricity, and we used it for powering up like low power devices. It could generate about maybe about 0.9 volts or 1 volt. If you use solar energy as your main source, depending on whether you're outdoors or you're indoors, that will make a significant difference in the amount of energy that is available to you. So there are different sources, and this is really an area in which you have to be very creative. You have to look at potentially what sources are available to you, how much energy you're going to be able to get out of them, and is it going to be enough to power up your sensor. So that brings us to the end of this lecture. These are a couple of references for you, and especially if you are interested in energy harvesting, the second book is a very good high-level overview of the different types of resources we have and the typical structures through which we can extract the energy. So let me know if you had any questions, and we will continue our lectures next week.